Hi and welcome back to this latest video in the series of videos that we're making here. Today we're going to be talking about microprocessors and microcontrollers and the differences between the two. There is a difference between the two, they're not both the same, but they are very closely linked, and we'll be showing some practical examples of microcontrollers in operation in different development boards, and also how we program them using different styles of programmer, and a few examples of actual circuits that I've built, for instance, as an example, with microcontrollers on board. So, but first let's do a little bit of theory, and we'll explain what's going on inside of the microcontroller and microprocessors themselves. So let's talk about the differences between microprocessors and microcontrollers. So let's just leave microcontrollers for now, because we need to understand what's happening with microprocessors first, and then we can talk about microcontrollers. That comes later. So for now, let's just have a look at this. Let's look at microprocessors by themselves. Now, the microprocessor itself isn't really a computer, so to speak. It's not a complete computer, but it is the heart of a computer. It's the bit of the computer that does all the work, really, and makes all the decisions about what happens during the process, running a program. So it is the very heart. In this area here that I've put in a box, that's really what's inside of a microprocessor. These other external areas you see in green and blue here, these are external to the chip, to the actual microprocessor itself. Now, the actual microprocessor is a physical chip. It's a physical package with pins on it. So inside this box here is everything that's inside of the microprocessor itself. So let's look at the different blocks within the microprocessor itself. There's a few things going on, but the main thing is this block here, I suppose, is probably the heart of the whole thing. This is called the Instruction Decoder. I've just call it InstDec for now. That's the Instruction Decoder, which actually takes instructions which are coming in through the data bus, if you like, from the ROM, which holds the program. And as it executes those instructions, depending on what the instruction is, it can go to a different address, it can put something in a register, it can do a computation, it can change the position of the address, or it can output more data to another device. So the instruction decoder is really the heart of the actual microprocessor to form the actual function of what the processor needs to do following the program. The other blocks that we have here, we have a set of registers. Registers are just very small memory elements, like usually they're 8 bits long, like 1 byte long, sometimes 16 bits long. And these are a bunch of registers which are used for all sorts of different internal functionality. You can use them as temporary stores for doing addition and division and that sort of thing. Or to copy one value from one position to another, you can usually copy to a register first before you go to somewhere else, and there are reasons for doing that. This other block here is the ALU, or the ALU, and that stands for Arithmetic Logic Unit. Now, the ALU is responsible for, or helpful for, doing mathematical calculations like plus, minus, times, divide, and other mathematical operations. This block here is the program counter, marked here as just PC. And the program counter, if you know what a binary counter is, it's basically like a big binary counter that can be set from the instruction decoder. It's basically clocked. As the clock signal drives the microprocessor, the clock is a square wave clock signal coming in. Usually this is either a crystal, or it could be an RC resonant circuit, something like that. But there's different methods of getting the clock into the chip, but basically it's a square wave oscillator, if you like, running in at various frequencies, like 1 megahertz right up to like 200 or 300 megahertz or something like that, depending on the chip. But basically it's a square wave oscillator. So that clock comes in, it then changes the instruction decoder to read the next instruction. Once that instruction is then completed, the program counter is then incremented to the next position, if you like, the next address location. If you understand binary counters, you'll know what that means. Every time you put a clock in, the output increments to the next binary sequence, the next value, if you like. And then the output of the program counter is basically our address bus coming out. The address bus, typically on older processors anyway, you'd have 16 address lines. We call these A0 to A15 on an older system, but basically is A0 to A15, which gives you 16 address lines, which is basically the output of the program counter, which is controlled by the instruction decoder, which is clocked from the incoming clock. This block here is the data buffer, and the data buffer is also read in and read out to, or written out to, the instruction decoder. The data buffer is bi-directional, as you can see there with 2 arrows going in both directions, and what that means is that you can send data out from that data buffer to peripheral devices, and you can also read it back in the other way as well, whereas the address bus is just one way, it's an output only. There's another little bit at the top here. This is the interrupt logic input, and the interrupt logic is basically an interrupt pin which allows the interruption of the flow of the program counter, so you can jump out of whatever it was that you were doing, save all of your values into various registers, like in other words the address where you were, and then do a completely different routine, another piece of code. When that piece of code is then finished, pop back to the original code that you were working on using the saved values in the register, and then continue what you were doing in the first place. So the interrupt is very handy for multitasking. You may want to do more than one thing at a time. You might want a series of things to happen at the same time, and it allows you to give the impression of a multitasking system where you've got two processors working at the same time, depending on how you write your code to operate from the interrupt logic or the interrupt pin coming in. Interrupts are very good for emergency situations or time critical situations where something has to happen immediately. You want something to happen straight away, like an emergency alarm or something like that. So you want it to stop doing what it's doing already and then go and do a different piece of programming. When it's finished, then come back and resume where you were. So interrupts are very, very useful and important, really. That's the microprocessor itself, the CPU if you like. So just to recap: instruction decoder, internal registers, an arithmetic logic unit, a program counter, which is basically giving us the address bus output, a data buffer, bidirectional, and the clock coming in from a crystal or from some other oscillator circuit. That's really what you get within the microprocessor. There's a little bit more in there as well, but they're the main blocks, just trying to keep it simple as possible. So coming outside of the microprocessor, as I said before, that's not really a computer by itself. If you wanted to turn it into a computer, then you have these other blocks here. What you need are extra blocks, like you need some sort of memory, like RAM, random access memory, which holds all of your temporary variables while you're running your program. It's also good for holding things like data tables and all sorts of information that you may want to keep and operate on, values that you may want to change, you may want to update them, you may want to delete them, and do all sorts of functions. You might even want to take your program and store it in there and run the program from there, but that's another matter. This block here is ROM, read-only memory, or EPROM in some cases. There's different types of ROM. It's basically classed as ROM, it's read-only memory, which can only be read from. You can't write to it. RAM can be written to and read from. It goes both ways. You can erase it, you can change it, and you can write to it, and you can read it later. But ROM can only be read. It's a permanent memory, and it can't be changed easily. The ROM critically holds your actual program, your firmware if you like, or if you want to call it compiled software. In other words, the instructions that get fed to the microprocessor, the actual program that does all the tasks that you wanted to do. And the instruction decoder is directly reading the data that you've stored into the ROM, your program. So the program's being loaded in, if you like, think of it that way. And the instruction decoder is working through one instruction at a time, going through, like going down a shopping list in a supermarket. You know, you start at the top and you work your way down. Well, it's the same thing really here. It's clocking the instruction decoder. It's addressing through a decoder device and taking the instructions one at a time from the ROM and loading it into the instruction decoder. When that's finished, it goes click to the next instruction. The program counter is incremented and the address bus again goes to the ROM to the next instruction, and so on. So it's reading instructions one at a time, going through the memory of the ROM. The I/O, or the in-out section, is really all about connecting physical pins, which I haven't written on here. Let's put some pins on here. Okay, pins. Yeah, so the I/O goes to the human world interface, physical pins that we can connect to LEDs, switches, all that kind of thing. That's really our interface connecting to the whole computer system. Switches, LEDs, buzzers, you could put oscilloscope probes onto there and look at the output pins and that kind of thing. And these are both inputs and outputs. So there could be 5-volt signals coming out, or there could be 5-volt signals or logic, high-low signals going in. It's bidirectional. And the only thing I sort of didn't really explain earlier as well was this green area, which is the address bus decoder. So as these address buses are changing and the instructions saying we might want to read a ROM, we might want to write something to RAM, we might want to send something to the I/O, depending on the instruction that we've been given from the program, it can select which region or which area of the address bus to select. So for instance, if we said our RAM section, just as an example, it can be anywhere, but let's just pick an example. If the RAM section was at the very bottom of the code space, of the very bottom of the address, starting at address equals 0. If this was all zeros from A0 to A15, binary value of 0, then if that's what I wanted to do and address the RAM, the decoder would be wired in such a way and set up in such a way that when we get an A0 to A15 0 address, then the decoder would say, okay, switch on the RAM, enable the RAM. These other two devices would then be off, so only the RAM would then be active for that single instruction. The instruction would set the address to where it wants to be, and then the decoder would say, okay, enable the RAM, switch the RAM on. These two would be off just for that one instruction. At that point, the data bus can then say, okay, let's set the RAM to a value, or let's read from the RAM. Again, it's bidirectional. The data bus is bidirectional. You can write and you can read. Let's say another instruction comes along, but this time we want to set an output pin. There's an instruction to set an output pin. So at this point, the instruction from the ROM program, the firmware, gets read in. The instruction decoder then says, okay, write to a pin through the PC, the program counter. The address bus then selects the page or the segment of address, the location, if you like, of the I/O device. And that might be at a different location, not at 0 anymore. It's at a higher number, like 256 or something like that, for example. So when it goes to address 256, represented in binary here, the decoder, the address bus decoder, would then switch on the I/O device. And these two would then be off. After having selected the I/O device, could then write the value that we want through the data buffer into the I/O device and switch on a pin, or switch on a combination of pins, or the other way around, read data in, check a pin to see whether it's high or whether it's low, and then send that back through the data bus that way and read the data in. So again, it's bidirectional, and the decoder is selecting the I/O device, switching off the RAM and the ROM at the same time. And of course the whole thing applies for any other device like the ROM. The decoder would be set to a particular area of memory space, or a particular area of the address bus, and the decoder would know at that point, or be set to at that point, to only switch on the ROM and switch off the RAM and the I/O. I hope you can see that the address, this is a critical part of the whole system really, the address from the instruction that and through the program counter, the address is actually crucial to selecting which device we want to select and operate with, whether it's RAM, ROM or I/O, or any other device that you might have on the bus. So the decoder is key to selecting which block we want, which device we want, and the program is written in such a way that we know where these address spaces are. We can actually select write to RAM, read from ROM, or set, read or write to an I/O device. And that actually creates a full computer. When you have these external devices connected, these external chips, decoder, RAM, ROM, I/O, and anything else that you might have in there, and the clock and everything, then at that point you have an actual computer rather than just the microprocessor by itself. Okay, so what about microcontrollers? Well, it's not difficult, because basically a microcontroller, again, is a single package chip. It's just a one chip device, just like the microprocessor is, but you have all of the external devices built in. It's basically everything that you see here in a single chip. It's all of that. Okay, so you don't necessarily need any external RAM, any ROM, or any I/O devices, or any decoder circuitry to select the addressing pages. It's all built in and more, because these days with microcontrollers you also have ADCs, analog digital converters, you have DACs, digital analog converters, which is all part of your I/O really. But it works with analog voltages as well. It's not just digital signals like we had on the microprocessor circuit with a basic TTL or whatever it is, 5-volt in-out signals. Microcontrollers have ADCs, DACs, that's analog to digital converter, taking analog signals in and converting them to a digital representation, or digital to analog converter the other way, sending a digital representation of a signal out through an analog pin. So that gives you real voltages. You could put an oscilloscope probe on there, or you could put a test meter and measure the voltage, that sort of thing. You've got other things like internal temperature as well. Sometimes you can measure the internal temperature. You usually have a sensor built in on nearly all modern microcontrollers have got that now. But yeah, so you've got other stuff. So really you've got all of this. You've got a microprocessor, decoder, RAM, ROM, I/O, And the clock circuit as well is usually internal on a microcontroller, can be external. You can have it connected to a crystal, but they also have a lot of internal oscillators as well, so you don't even need an external crystal. You can actually just use the internal oscillator, and all that's built in. And these extra functions and some other stuff as well. Some of them have more built-in, better mathematical functions, like maths processors built in, like MPUs and all sorts of things. So, you know, it's just getting more and more advanced as time goes by. So I hope this gives you an overview of an actual microprocessor unit, or CPU, the internals of the CPU, and basically what's going on here. Then you connect that to external devices, a decoder to select which device you want to address, RAM, ROM and I/O, and then you've got your actual physical world pins, in and output pins. It could either be set to an input or it can be set to an output. That can be as big as you like or as small as you like. You could have 100 pins on there, or you could have one pin. It's entirely up to yourself and up to your design of your circuit, depending on what you're trying to do. Then you've got a microcontroller, which is just a single chip device in a single package. And it has all of that and some, with the ADCs, DACs and temperature built in, all that sort of thing. Some have temperature, some don't. Depends on the chip. So with all that said, let's go and have a look at some practical devices, and we'll go and have a look at some chips and some boards and see what they look like. Okay, here's something that I actually built myself in around about 1985. So this is pretty old. And it was part of a radio system. It's actually a repeater control card. It's designed to turn on and off transmitters and generate Morse code to be sent over the transmitter as well, and it controls it in a particular way, what we call a repeater, where you can connect two radios together, one listening and one transmitting at the same time. Point of this is a microprocessor here. It's just a single chip. It's a big chip. It's got quite a lot of pins on it. This particular one happens to be what they call a 6502 processor, 6502. The same processor that was used in things like Commodore 64, Commodore VIC-20, lots of computers actually back in the 80s. So I built this using one of these. As I say, it's all very old technology, but it's good to see this. The reason why I'm explaining and showing this is because it gives you an appreciation for everything that's actually inside of a microcontroller, and I'll come to that in a moment. So this is just the microprocessor. As I say, it's a 6502. It's an 8-bit chip, so it can handle a 8-bit data bus. I'll explain some of the other parts here. Well, this is our ROM. This is an EPROM actually, and I've got a little sticky label on the top of it to stop ultraviolet going through. It's got a little quartz crystal window behind that sticker, and you can erase these chips using an ultraviolet light. So to stop sunlight from erasing the chip, put a sticker on the top, like a metallized sticker, and it stops the light getting in. That's what that's for. And I've written my call sign on there as well. So that's holding the program to do the entire job of running the computer. So that's the EPROM holding the firmware or the program, and that's been programmed already by a programmer, an EPROM programming device. And this chip here is the RAM, which, if I remember right, is 2K, 2000 bytes worth of information. That's 2K as well actually. So that's got 2000 bytes worth of program or firmware, and that's got 2000 bytes of memory or RAM locations. We've also got a little bit of I/O here as well. We've got a couple of logic gate chips here. One is a set of latches, what they call latches, which is basically you put a signal in and then it keeps the signal on. That goes to these pins here, which did various functions like turn the transmitter on, turn the transmitter off, send Morse code out as a digital signal, like what we call an ident signal. Another part of the I/O is the input pins. That measures other things like whether the receiver is receiving or not, things like that. There was other things as well, but that doesn't matter right now. So they were doing that's the in-out section, that's the RAM, that's the ROM, and we've got a chip here, and that's the decoder, which takes the address from the microprocessor and segments it, if you like, switches, either puts on the I/O section, puts on the RAM, or puts on the ROM, depending on the value coming through the address bus. And up here we'll have a little bit of logic, TTL logic, for the clocking circuit. That's the clock with its little oscillator there, and the clocking arrangement then drives the clock input, which internally clocks the program counter, if you remember, to read the values from the firmware. And that's basically, put it all together, all these devices on a board, and you end up with an actual computer. Now that really is a definition of, that could be definitely classed as a computer. You have processing, you have ROM, RAM, and in-out decoder as well. So that is actually classed as a full computer. And I can show you the back just for laughs. This is what we did back in the day. That's a handmade PCB that I did with a marker pen. If you watch one of our first videos on making PCBs and using prototype boards and that sort of thing, I explain how you make basically a PCB like this. But as you can see, we've got a lot of wire on here as well, because this was in the day before I could do double-sided boards. This is a single-sided board. You know, there's no tracks on the top. There's only tracks on the bottom. So in order to get, you know, wires and tracks to cross each other, I had to use wire links. So you've got a combination of copper tracks, the actual PCB itself, and then you've got the actual wires which cross point across that. Well, you may have come across these before. This is an Arduino development board, and it's got a single microcontroller on it. Now this is where we start talking about microcontrollers. There isn't actually that much else on the board except for a little USB interface here with a USB interface chip. You've got power in, and you've got a crystal here for the clock. This particular one has a 16 megahertz crystal on it, and everything else is pretty much pins. Okay, there's not that much on it, so I think you'd appreciate that's a lot smaller and a lot simpler, and incidentally it's a lot faster, and it has much more memory and everything than the board that I built back in 1985. We've come a long way. But the important thing here is that this is a microcontroller, and everything that you saw on the other board is all built into here, and way more as well on top. This has the RAM in it, it has the ROM, it's a microprocessor if you like, with the ALU and the program counter and the encoder and everything, and all of your in-out pins in one chip. Okay, it's all in there. So you program that, you use USB in this particular case, and that puts the serial data through this with an external computer and some software on your PC, and you can program this to do all kinds of jobs. These are all of your in-out pins. You've got lots of in-out pins, and some of these also have analog input and analog output pins on them as well. It's got an ADC built in, just to give you, a bit of an idea of how far we've come. All of that is now in one chip, and these are very cheap. They're about £1 each. That's all they are, £2 maximum. Very cheap indeed, and you get all of that. It's got way more memory than the one I built. It's got way more RAM and ROM and in-out pins as well. It's just better in every way. And you can buy these development boards for, I don't know, probably like £10 or something like that, whatever the whole board is. Underneath it's just a PCB on the bottom there as well. So that's just showing you how far we've come, and that is a microcontroller, everything built inside. And the processor actually used here in this particular case is an ATMEL ATMega 328P, and that's what they use in the Arduino development boards. Moving along, things are getting even smaller. So now we actually have a microcontroller in a surface mount device, and again it's the entire computer with lots of memory, lots of RAM and ROM, and loads of in-out pins. Look at all these pins here, loads and loads of in-out pins. Plenty to do here, plenty of things that you can connect to this. They're all in-out pins, well, most of them anyway. Some of them are power connections and stuff, but that's basically correct. Everything is in this single package. This other chip here is not to be confused with that. That's just for the USB interface. That's got nothing to do with the actual computer itself. And you have a clock, and you also have another clock here. Everything in one chip. Again, a microcontroller. This particular one is called an STM32L1. It's a very good device, to be honest. And this particular development board, they've used one of these chips, which you program through USB, again to your PC with the correct software. You can write the software in C or C++, and you can what they call compile the software, and then that comes through the USB socket, and can then program internally the ROM or the EPROM, whatever it is inside of these, to program that with the firmware for the computer to work with. On this particular board, we also have a little LCD display, so you can put on characters. It'll actually various indicators. You can display anything you like really on there, driven from the firmware, and that's driven directly by some of the in-out pins. A lot of these in-out pins connect directly to these pins of the display, and with the right combination of pin, depending again on your firmware, you can have various characters, like hello world and that kind of thing. So that's an STM32L1. It's a surface mount device, getting smaller all the time. Here's another microcontroller development board. These are very popular at the moment. This is the Raspberry Pi. You're seeing these all over at the moment. A lot of people like playing with these because these particular boards have got lots of inputs and outputs. You've got lots of USB sockets for USB devices. You've got an Ethernet connector for internet. The later versions of these have wireless on, so you can connect to the internet wirelessly as well. This one doesn't, it's an earlier one. I think this is a Model 2. But you've also got HDMI connector on here, which allows you to plug it into a television monitor, into your TV, or into a computer monitor for an actual display, just like as if you would plug a PC into your monitor. And this is actually a complete computer on a board, if you like. The heart of it is, yet again, a microcontroller. This particular one's a Broadcom that they've used on here, which is like a QFN chip, which is soldered directly to the board, and is even more densely populated than the ARM chip from the STM ARM chip on that one. It has even more memory, more RAM, much more RAM. It's got about 1 megabyte, I think it is, I'm not too sure. More ROM for putting in your firmware. Faster still, faster clock speeds as well. They just keep getting faster and faster as time goes on. But basically these all have the same thing in common. They all have a microcontroller. That's a microcontroller chip, that's a microcontroller chip, and that's a microcontroller chip. They're just getting quicker as time goes by, and this is now an old board. You can get them even faster and even with more memory and higher speeds even more as time goes by. But basically that's what microcontrollers are all about, and this is in itself an entire computer on a board that you can physically, you can plug a USB keyboard in, you can run Linux on this, the Linux operating system. You can load onto this. You've got a mouse, you've got graphics on your screen, just like Windows or Linux on a PC, for instance. Yeah, getting better all the time. Oh, and lots of in-out pins as well, so you can experiment. You've got ADC, DAC, and I/O, just like the other boards as well. Another type of microcontroller that you could well come across quite a lot these days is the MicroChip company make a chip called a PIC, and that's this particular one here. They do a whole range of surface mount QFN chip and DIL dual inline packages like this particular one. So this is like a bit of a basic one really compared to the ones that they're bringing out now, which are far superior and much faster. But this particular one I put on a circuit board a while ago to make a pan tilt system to move a camera around on a tripod using these remote control position motors. Okay, so that's what this does, and this has got firmware runner to drive those motors. It operates through CAN bus from an external device, so basically it's like a remote control, if you like, to alter the motors. That's what the task of the board is. But the main thing here is the actual chip, and as I say, this particular one is a PIC 18F, I'm forgetting the number, 2585 I think it is, on this particular board, made by Microchip. So these are very popular as well, microcontrollers. See these all the time. So there's different manufacturers of microcontroller. You've got your ATMEL, Broadcom do one, there's the ARM range, STM, PIC, and there are others as well. It's not limited, these are not the only ones. There's plenty of different types of microcontroller out on the market. But they're essentially, the whole point of this video really is just to give an appreciation for what it's all about. And if you look back at the first part of the video, you can appreciate there's a heck of a lot of circuitry inside of each one of these microcontrollers. Got the entire microprocessor device, the RAM, the ROM, the in-out, and other things as well. Sometimes they've got built-in temperature sensors actually inside of the chip, where you can actually monitor how hot the chip is getting, and you can report that back in real time, for instance. So there's things like that. They've built-in sensors. They've got warning detectors, like if the voltage goes too low, the supply voltage goes too low, it can self-detect whether it's going to have a problem or not before it happens. So you could report back if there's going to be a problem with the supply voltage. All kinds of things like that. What they call brownout detection and stuff, and it's all built in. It's just getting better all the time. And they're putting more features in. The chips are getting more and more dense, more memory, more RAM, more ROM, faster clock speeds, so you can get through the program faster. You can get more tasks done, more interrupt signals, so you can do, like, if you like multitasking or the appearance of multitasking. It's just going to get better all of the time. Who knows what's going to happen in the future? It's just going to get faster and probably smaller as well. And here's just a little practical demonstration of the sort of things you can do with microcontrollers. Here we've got the ATMEL ATMega 328P microcontroller here on a board, bit of error board. I've got another chip on here which is basically just a motor controller, like a buffer chip, and this is a stepper motor. Got a stepper motor connected and I've got a little bit of white tape stuck on the top here just so you can see it move around. We've got an LCD display here with some characters showing at the moment, and that's being controlled from the ATMEGA 328, and we've got a little, almost like a telephone keypad here. There's some numbers on it. These should really have little arrows on because we can turn the motor left, right, and that sort of thing. But I just haven't bothered doing that. We've just got numbers on. So what we can do is push some buttons, change the stepper position of the motor. And you got to remember, the whole point of this is that this controller chip is doing absolutely everything. It's sending data to the screen through an I2C interface bus, 2 wires, which is a serial information system. Very simple, just do 2 wires. It's also sending the control signals to the motor controller chip, the buffer chip, which is working on 24 volts at the moment, and that comes through this cable here through a connector to the stepper motor. So the whole thing, the keyboard, the LCD display unit, and the motor is all being controlled from this chip. You might be able to just make out as well. There's a little crystal oscillator on there. There's a little 16 megahertz crystal, and that's the clock driving the processor. This has been programmed, of course. I've already programmed this earlier through an in-circuit programmer, a little header here with a programming device. So I wrote some software beforehand, compiled it, and then programmed it into the ROM area of the chip. Okay, so our software, I'll just tilt this up, our software is now in this ROM area here, okay, and ready to go. So let's have a play. Let's try some buttons. So I think I can make this turn around. I'll hit a button. There you are. And that makes it, I think that's 1 full revolution, which is 200 steps. If you can see that there, that's 200 steps. Yeah, so that's 1 whole revolution. That's 200 steps, and it says minus 200, if you can see that or not. Try going the other way. That's took us back to position 0, and then this should take us round another full revolution, and there you go. So that's now plus 200. So every time you press that button there, it says do 1 full revolution of 200 steps. Now it says 400. So, and I think we can potentially bring it back to a 0 position by pressing 0. Should come all the way back. There you go. And now it says 0 again. And you can do other things like you can single step it, like 1 step at a time, and you'll see it turning very slowly. Or press it the other way, and it will come back again. There you go, back to 0. So all this is being controlled by this microcontroller. It's all clever stuff. And when you consider this chip probably only cost about £1, it's pretty good. You know, you've got your RAM, you've got your ROM. There's a program counter in there, which is all internal. You don't even need access to the address bus anymore because it's inside. But crucially, all of the I/O pins are available. Lots of I/O pins, and it's the I/O pins that the in-out pins that we're using to drive the motor controller chip there, to drive this motor controller chip here, which then produces a phased output to drive the stepper motor here. So that's a practical example of something that you can build yourself. It's all on Vero board, pretty cheap. Probably the most expensive part here is probably the display. I think that was about £10. I'm not sure. I can't remember now. It was a while ago. And the keyboard was about £2.50 or something. So it's not a lot of money, and that's actually quite a strong motor as well. You know, you could use it to turn a camera around or to turn a lamp around or something like that. You know, you could use that for all sorts of things. And that's all being pre-programmed software as firmware into the actual, what we refer to as the target device. When we talk about the target device, that's basically the device that takes the software or the firmware. Okay, so there's a bit of a practical example of using microcontrollers. I'll show you some programming devices. This is basically an EPROM programmer. It's also a microcontroller programmer. These are quite cheap. You can pick them up for about £30. It comes with an application software that you put on your PC. It connects through USB, so you just connect this to your computer. That has what they call a zero insertion force, a ZIF socket, ZIF. Put the chip in there, whether it's an EPROM or whether it's a microcontroller, and then you lock the pins like that with that little lever there, and it grabs all the pins, and then you program the chip, and when you're finished, you flick that back and you can take the chip back out again. So that's an EPROM programmer. If you're working with old equipment, it's very handy because old equipment tends to have EPROMs in it if it's got a computer, and it means you can back up firmware, you can copy firmware, you can repair, you know, certain systems and make changes, that sort of thing, or build new devices. So these are great. They're not very expensive. As I say, it will actually program a microcontroller as well, depending on the chip that you're using. This one is this is an AVR programmer. This is designed for programming ATMEL devices like the Arduino that I showed you earlier. And this has got a little header on it. Again, it's USB in from the computer. It comes with some software from your PC through the USB connection, and a little ribbon cable, a little connector on the end of there, and that can go what they call to an ISP, which is an in-circuit programmer DIL header. You can put that onto your board and you can program the chip while it's actually in the board. In fact, I've got one over here. This is a board I made some time ago. It's a memory device for a radio, and this has got two ATMEL chips on. These are surface mount versions. These are both microcontrollers. There's two of them on here, and you can program them through these DIL headers here. So using this programmer, you can actually program those chips by connecting to those DIL headers, what they call ISP connections, in-circuit programming connections, because the chip stays on the board. You don't have to remove the chip, thank goodness, because they're quite difficult to solder these. So, you know, they stay on the board and you program it while it's in circuit. That's an in-circuit programming connection. This one is this particular one is called a Pickit 3 from Microchip, and Microchip do their own range of microcontrollers, you know, like the PIC I showed you earlier. And on this particular board that I made, on here, you'll see that it actually has a header here, a single inline header, and that's actually a programming header for the programmer to plug into. So the programmer actually connects into there like that. That connects to the computer through USB, again with its own firmware, with its own software, and that programs the chip internally with your firmware. So there's a few different programming devices, and I use all three personally, depending on what it is that I'm actually working on. They all have their own purposes. There are other programmers as well for different devices. The STM, they have their own system. A lot of the STM system controllers you can program through USB. You don't really need any external programmer at all, but you can program with their own dedicated programmers. You tend to find that each manufacturer of chip has their own method of programming the chip, so you end up with like a collection of programmers if you're using different chips, you know. But these are probably the common ones, I would say. A lot of you know, people, or if you're into repairs, or if you're building your own small projects, these are the sort of programmers you tend to end up with. You can get much more complicated ones as well, you know, with a little more functionality, built-in emulators and stuff where you don't even need the chip. You can test your firmware into the emulator without actually having to physically connect a chip to it. Right, well, I hope that gives you a bit of an overview of microprocessors and microcontrollers, and I think in the next video we could be looking at a little bit of software, the sort of software that you would write in order to get controllers to work. We'll maybe do a few blinky examples and that kind of thing. We'll see how we get with that. I hope you've enjoyed the video, and thanks for watching, and it's the next time.